So let's continue where we left off with the last video. So let's continue where we left off with the last video with states of matter. Now, going from solid to liquid to gas, solid to liquid is called melting or fusion. Liquid to gas is called vaporization. We can go in the reverse direction, where we go from gas to liquid, which is a phase change called condensation, and liquid to solid, which we call freezing. You may be familiar with those terms. You can also go directly from solid to gas. We call that sublimation, or gas directly to a solid, and we call that deposition. Those phase changes occur only under a very specified set of conditions of pressure and temperature. All right, so what determines the temperature at which a substance will, let's say, melt or vaporize or go in the reverse direction? What determines the temperature at which that will occur are the strength of what we call intermolecular forces. Those are electrostatic forces. Those are the attractions between molecules. So melting and vaporization and the reverse direction would be controlled by these intermolecular forces and the variety of strengths. And that it will be dictated by the structure of the molecule, the polarity that's in the bonds of the molecule. And this is something that will go into considerable detail in Chemistry 1342, which is the second semester. However, we can summarize that as just how sticky molecules of different substances are for each other. So if two molecules are very sticky, it's going to take an awful lot of energy to move them apart, to break those intermolecular forces between those particular particles. So let's take a quick look at a short video on phase changes, changes in states of matter.
When heat is applied to a solid, its temperature and vapor pressure increase with increasing temperature because the molecules of the solid have increasing kinetic energy. At the melting temperature, heat is absorbed as the solid is converted to liquid at a constant temperature. When melting is complete, the temperature of the liquid and its vapor pressure increase. At the boiling point, temperature remains constant as heat is absorbed to convert the liquid to the gas phase. When all the molecules are in the gas phase, the temperature again increases as the gas phase molecules acquire additional kinetic energy.
All right, let's talk about substances. One of the things that we do in science, and in chemistry in particular, is we characterize matter according to the type of matter it is. So a pure substance is characterized as matter that has a fixed composition. That is, there's only one kind of substance, and it has distinct properties like boiling point and melting point, density. The substance will have these unique properties to that particular substances. So pure substances contain only one kind of matter, and those we can further characterize this as pure elemental substances or pure compound substances. So if I look at a periodic table, and this is the periodic table of the elements, each of these symbols represents one particular element. So Zn is zinc, and if I only have atoms of zinc, and remember atoms are the smallest unit of an element, if I only have atoms of zinc, I have a pure elemental substance. The same thing could be true for oxygen. If I have only oxygen atoms, I have pure oxygen. And that's true for any of the elements, something that's often sought out after historically and to this day, pure gold. And so if I have only atoms of gold, I have a pure elemental substance that we call gold, and its symbol is Au. The other type of pure substance can be a pure compound substance. So this is the structure of water. It has one oxygen and two hydrogens, and that's a fixed composition. I can't add a hydrogen to H2O. I can't add an oxygen to H2O and have the same substance. Water has a fixed composition, H2O. And this is known as a compound. A compound is a substance composed of two or more different elements. And so if I have pure water, I have only molecules of water. So elements, things like H2, that's what we call a diatomic molecule, but it's still just hydrogen. If you only see a single symbol, we're talking about an element. This is sodium and argon and oxygen. Oxygen is also diatomic in the way that we breathe it, the way we consume it. It loves to run around the planet as a diatomic molecule. That's when it's most stable. Substances that cannot be decomposed into simpler substances by chemical means. So I can't decompose sodium, argon, oxygen, or hydrogen into something that isn't hydrogen, sodium, argon, or oxygen by doing chemistry on it. So a substance that cannot be decomposed into a simpler substance by chemical means, that's what we call an element. That is our test as to whether something is an elemental substance. Compounds, on the other hand, are composed of two or more different elements, and I can do chemistry on a compound. This is water. Water is a compound substance. It's got a fixed composition of one oxygen and two hydrogens. You know it as H2O. That's how you tell it's a compound, because there are more than one different element in the chemical formula for that particular substance. Now, I can do chemistry on water, and I can separate the hydrogen from the oxygen. I can separate oxygen and hydrogen from each other into O2 and H2 gases, which have completely different properties from water. Water is either ice or liquid or a gas. So this is a pure compound substance. And just remember, it's composed of two or more different elements, and I can separate these elements by doing chemistry. That means it's a compound. You need to know a number of the elements on the periodic table. We'll start off and we'll just name a few. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, and krypton. So these are elements that you absolutely need to know the symbol of and the name of. You don't need to know their atomic numbers, which we will get to, but you do need to know their symbols and their names with proper spelling. That's not quite enough, so we're going to add a few. We've got rubidium, strontium, barium, cesium, tungsten, platinum, gold, mercury, lead, tin, and iodine. Now, it's not going to hurt you to know that this is xenon, and this is antimony and tellurium, polonium, bismuth, radon. These are all elements that are in your world, but they are not as essential as the elements that I have outlined in the red boxes. So please know their symbols and their names with proper spelling. Let's talk about the diatomic molecules. Now, these are elements that exist naturally as a combination of two atoms, and here they are. There are 7 of them: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. They're easy to recognize on the periodic table. Let's take a look at what it means for a molecule to be diatomic, or an element to exist as a diatomic molecule. Here is a chlorine, which is inherently unstable. We'll get to why later, but it's inherently unstable as a solo, what we call a monoatomic element. And so what chlorine does in the presence of other chlorine atoms is they will hook up and they will bond to another chlorine atom to become Cl2, which you can see as a diatomic molecule. And all of these other atoms do exactly the same thing. They're inherently unstable as monoatomic atoms or elements, and so they hook up with themselves or with another of their type as a diatomic molecule. Here is O2. You don't breathe just O, you breathe O2. Here is how you recognize or easily identify which are the diatomic molecules. We'll start with hydrogen over here, and you'll just have to remember it, but it's easy because it's atomic number 1. It's the first element on the periodic table to the far upper left. And then you go over here to nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. I told you there are 7 diatomic molecules or diatomic elements, and they make on the periodic table the number 7. I know there's only 6 here. 1, 2, 3, 4, 5, 6. You have to add hydrogen. But these are your diatomic elements. Please know them. Know that sulfur and phosphorus and silicon and aluminum, they're not diatomic. These are the diatomic elements for which you're responsible. Compounds are a combination of 2 or more different elements. This is water. It is a compound. It has the formula H2O. Molecule of water has a fixed composition of 2 hydrogens, 1 oxygen. It contains 2 atoms of hydrogen, 1 atom of oxygen. That is a compound. That's what this compound is, the word that we use to define a substance that has 2 or more different elements. So if I had this would be another compound, which you may be familiar with if you've ever looked on your medicine chest and you see hydrogen peroxide. It is a compound that is not water. Now, it may look a little bit like water. It's clear. It's a liquid at room temperature. It's a compound, but it is not water. Okay? Here is another compound, C6H12O6. If you're a biologist or you've had biology, you may be familiar with glucose. And glucose is a compound. Why is it a compound? Because there are more than one different element that are chemically bound to each other in a single unit of that substance. All right, let's go ahead and summarize what we've learned so far. It's very difficult to image on the particulate level, on the atomic molecular level, elements, compounds, and so what we do is we use animations or drawings quite often to visualize them. And we imagine atoms as being these little spheres. And if all the spheres have the same color, we know that these are atoms of a single element. That's our representation. And so we simply call these atoms of an element. When we have more than one atom that are chemically bound to each other, as indicated in this fashion, where we have the 2 blue spheres are connected to each other, that's a molecule. Now, a molecule is a structure that consists of more than one atom. You can have molecules of elements when the colored spheres are the same color, depicting that this would be, let's say, something like nitrogen N2 or O2, could be H2 or Cl2. We do select particular colors for different elements. This is most closely resembling, let's say, N2, nitrogen, and it is a diatomic molecule. And so we would call this a diatomic molecule. And that is simply more than one atom that is connected to the same type of atom, and so we would say this is a molecule. And remember, a molecule is a structure consisting of two or more atoms that are chemically bound together, and if the two atoms that are bound together are the same color in this depiction, then that is a molecule of an element. So a molecule is a description of the smallest unit of a substance, and it's just two or more atoms bound together. Now this is the molecule of a compound. That's what it's depicting or representing. We know it's a compound because we've got three green atoms connected to one purple atom. So this could be nitrogen, these could be three hydrogens, or this could be phosphorus, these could be three fluorines. In any case, this is a molecule because it's a discrete unit consisting of more than one atom that's bound together. It is a molecule of a compound because the atoms that are bound together are not atoms of the same element. You got a purple element, purple atom, and you have three green atoms here. So that's two different elements, and we know from previous discussion that that indicates a compound. Molecule means that this is a smallest discrete unit. So this is a molecule. That is, this unit is a molecule because there's more than one atom chemically bound together in a discrete unit. And since the atoms are different, we call it molecule of a compound. Now this is what nature does. Nature is a mixture. You have mixtures in your body. You are composed of compounds. There are elements in your body. You're breathing in oxygen. You're mixing that through your lungs, through your alveoli, into your bloodstream, and that gets into your cells and drives the cellular respiration. So you are a mixture. Everything in nature is really a mixture, and in this case, we've got a mixture of compounds. We've got a mixture of diatomic molecules, and we have a mixture of atoms in this particular space, and that's what this is indicating. So this is a mixture of elements and compounds. So referring to the previous slide, one unit of each substance listed below would be, so this is H2. We know it's a molecule, and it's a molecule because there are two atoms chemically bound together. They are the same atoms, so we say it's a molecule of an element. This is, if I'm referring to the smallest unit of H2O, the smallest unit would be a molecule of a compound because water is a compound. It's composed of two different elements. You've got oxygen in a, you've got oxygen in a 1-to-2 ratio with hydrogen. And so a single unit of water, the smallest unit of, this would be molecule of a compound. Compound because there's two different elements combined together. Now, initially we fib sometime, but we clear it up later. Right now you might think, well, this is a compound, and you'd be absolutely 100% right. And if you were talking about a single unit of this compound, you would think of it as a molecule of a compound. This is actually, we're going to learn a little bit later in Chapter 2, this is an ionic compound, and it's actually a crystal structure. There are no discrete molecules of sodium chloride. There are big ordered arrays of ions in this ionic compound. For the time being, molecule of a compound will be just fine. Now, argon is a monoatomic element, and so it runs around as single atoms, so we would call this an atom of an element, because there are, if we're talking about the smallest unit of the substance that we call argon. This is glucose, once again, and a single unit, a discrete unit of glucose we would call a molecule of a compound. Why is it a molecule? Because it's the smallest discrete unit of the compound. Why do we call it a compound? Because there's 2 or more different atoms. We've got carbon, hydrogen, and oxygen chemically bound together in 6 to 12 to 6 ratio.